we're back. Today's topic is on weather forecasting. We're going to look at some weather maps and play around with some numbers, practice some gradient. All right, first of all, meteorologist. These are scientists who study and forecast the weather. And most of you have seen meteorologists, of course, on the 6 o'clock news or on the Weather Channel, but there's lots of other meteorologists besides just those people who are on television. Now, forecasting the weather involves putting together all the pieces we've learned so far. We'll need to analyze the data, interpret what the data is telling us, then use forecasting skills to make the right predictions. And this is a non-stop process. They're doing this all the time, 24/7. And nowadays, computers are involved big time. All right, some field values. Now, we've worked with field values in the topographic maps unit, and we've looked at some of the particular weather variables here in this unit that we're going to be making field maps with. Temperature, air pressure, relative humidity, dew points. All these things can be shown with isolines. And remember, isolines are any line connecting points having equal field values. And in this particular unit, the things we really stress are isotherms, which are temperature lines connecting points of equal temperature, and isobars, lines connecting points of equal air pressure. And there are others, and nowadays on computer weather maps, you actually see a lot of these things not with lines but with colors. So, question on this map: what type of isolines are shown here? And you can see 996 starting at the center of the low, working our way out from there to 1000, 2004, 1008. These are not temperatures. These are air pressures, barometric pressure, and these are isobars. Contrast the wind speeds at A versus B. I think you guys already get the gist of this. B, the lines are very close. The isobars are very close. And this means we have faster winds here than over at point A, where the isobars are very far apart. There's a big distance between these, so there's slower wind speeds there. And we've learned this formula earlier in the year in the topographic maps unit, but once again, gradient rears its head. Gradient is the change in value between 2 points divided by the distance. Your reference tables has that formula right in the cover. Change in field value over distance. An example of gradient is how steep a hill is. How much does its altitude change over a given distance? Remember, we had that whole discussion about which side of the hill would you rather take your grandmother up, and we looked at the distance between the lines in the map. The formula to calculate gradient is on the front of your front cover. I already mentioned this, of your ESRTs. Two types of gradient we normally look at in weather, once again, are temperature gradients and barometric pressure gradients. And they're both calculated in the same way, just different numbers. So first you find the difference in the field value. It's either going to be a temperature field or a pressure field, and divide that number by the distance from the scale on the map, and it's either going to be in kilometers or in miles. And it's easy to do this. If the ice lines are close together, remember that indicates a steep gradient, and if they're widely spaced, you have a shallow or gentle gradient. And important, the pressure gradient is directly related to, and we all know this, wind speed. And that's what we just looked at in that last map. The closer the isobars are to each other, the faster the wind speed. Okay, moving on. So let's take a look at this map, calculate the pressure gradient between points A and B. So we need to know two things to find the pressure gradient. We need to know the change in the field value, the change in the air pressure between A and B, and we need to know the distance. In this case, the map's in kilometers between A and B. I've already found the distance ahead of time here, and that distance is exactly 1,000 kilometers between points A and B, so we know that. Now we need to find the other thing, which is the change in the air pressure. So I'm going to follow point A along this isobar, and I see it's at 1,016. So we know that number is 1,016 a day, because everywhere along this line is 1,016 millibars. That's the whole point of an isobar. Okay, point B, follow this around, and we see that it's at 1,000 millibars. So that makes the difference pretty easy. It's just 1,016 minus 1,000 millibars, and we get 16 millibar difference. So we're going to take that number, 16 millibars, and our 1,000 kilometers that we found as the distance between A and B to the next page. All right, the formula. And this is a weak spot for a lot of you because they don't like to write this stuff out. But it's free. It's free points. Gradient is the change in the field value over the distance. And so for substitutions, we're going to take our 16 millibars. That is our field value. That's the change between the two air pressures. And divide it by our 1,000 kilometer distance. And make sure you divide correctly here, because I don't know how many times I've seen students, they have a small number on top and a big number on the bottom, and for some reason they plug in 1,000 or the big number into the calculator first, thinking that's how you divide. But no, that's not how you divide. So I have a calculator off here on the side here. I could actually do this on the smartboard too. But when I do this, I get a very tiny number, 0.016 millibars per kilometer. Units are important. The way you derive these units is just by looking over here. Millibars are being divided by kilometers. All right, so hopefully you see that example. Okay, we're going to use this map. We're going to go back and forth and answer some questions now. And we can see we have some fronts here. And we have a low pressure area, high pressure areas, and lots of isobars. So first question, which city has the highest wind speed and what is it? So we take a look at the map, and I'm looking for feathers, and I see that Cheyenne, Wyoming has 3 whole feathers, which is 3 times 10 is 30 knots, 30 nautical miles per hour. So number 1 is Cheyenne, and it's 30 knots. All right, number 2, what type of front recently passed Albuquerque? Or as Bugs Bunny would say, Albuquerque. And it looks like, as far as the fronts go, looks like this is a cold front. And it's the thing that's recently passed by Albuquerque, at least most recently. So that's an easy question. And that would be a cold front. Okay, which city has the highest chance of rain? All right, this is a good question. So I'm going to look around here for first overcast skies, and I see Chicago has an overcast sky, Memphis, Omaha, Pierre, and Miles City. Because if it's raining, it's most likely going to be overcast or 100% cloudy. Next, I'm going to look for the air temperature and the dew point. And remember, the closer they are, the higher the chance that we have 100% relative humidity and precipitation going on. So I see Memphis, they're still pretty far apart, like 11 degrees apart. Chicago, they're like 3 degrees apart, 57 minus 54. Omaha, they're pretty close, but not as close as hey, look, Pierre, 52 and 51. Miles City, they're a couple degrees apart. This has the closest dew point and air temperature, so I'm going to pick Pierre because the air temperature and the dew point are almost the same, and it's overcast. Okay, what will happen to the air temperature, cloud cover, and wind direction in Memphis in the near future? So air temperature, cloud cover, and wind direction. Memphis, Tennessee. All right, let's get rid of some of this stuff so we can see what's going on. And in Memphis, looks like pretty soon, cold front's going to be passing by. And right now it's overcast, cloudy. And the wind is from a southerly direction. So I'd say after it passes, if we look at some of these stations back here, you can see the wind switches around from a southerly direction to a more westerly direction. And the skies start to clear. temperature, because it's a cold front, should drop. And we see 79 in Memphis before, and 57 in Springfield, and 54 in Wichita after. So if I was to make a forecast in the future, I would say that the air temperature is going to drop, the cloud cover is going to decrease or get more clear, and the wind direction is going to shift from the south to the west. And that would be a decent forecast for those three weather variables. Okay, the next question. Calculate the temperature gradient between Miles City and Pierre. Miles City and Pierre. Now, I've already done the distance between these two cities, Miles City and Pierre. And down here, it's in kilometers again. Turns out it's 500 kilometers. And the temperature gradient is what we're being asked to find here. So we have 45, and I can't read the other one. Got to erase that for a second. And 52. So those are the two numbers we're dealing with. And the difference between 52 and 45 is 7 degrees. And these are in Fahrenheit. So 7 Fahrenheit. All right, now let's bring everything to the next page. So we have a distance of 500 and a temperature change of 7 degrees Fahrenheit. So our formula, gradient equals change in field value over distance. And substitutions, we have, remember our temperature goes on top, 7 degrees Fahrenheit change, and the distance is over 500 kilometers. Kind of strange here that we're mixing units between English and metric. I don't really like to do that, but that's what the numbers are in, so we're going to do that anyways. And when we divide this out, 7 divided by 500 gives us a very small number, but it is the answer, 0.014. And once again, we have degrees per kilometer. So there's the units. Don't forget to use correct units. All right. Moving on. Now we're going to be doing a lab on this soon, but synoptic weather maps. This is kind of like a bird's eye view of the weather, and it gives us a brief synopsis of everything going on all at once. Now the weather map right here that you see is a commercial map used for non-scientists for the most part. It shows the lows, remember the cyclones, and the highs, the anticyclones, along with their associated fronts. And it shows precipitation in green, some isobars in like a very light white color here. And we can even see the nice shape here of our low pressure cyclone. It's pretty cool actually how it comes out exactly like you've been taught. But you obviously can see in this map that you can add a lot more detail, a lot more data to a weather map. And here we have a different day. This is a surface weather plot, and it shows cold fronts, warm fronts, highs and lows, isobars, but it also shows all those weather station models. Lots of information there. You can even zoom in different parts of the country and get some information on weather station models. So here we can find wind direction, wind speed, air temperature, dew point, air pressure, cloud cover. Okay, forecasters generally watch the direction a cyclone's been moving and assume the system will continue to move in that direction at roughly the same speed. And this is called the storm track. And you can calculate this by measuring the distance the storm has traveled and dividing it by the distance dividing the distance by the time it took to go that far. And you might be asked to do something like this, where you can see that it's traveled a certain distance, and you can figure out somewhere on that map how long it took to do that, and you have to divide distance by time to get its speed. Over North America, our storms generally travel northeast or southeast because of the prevailing winds blow from west in general to east. They're steered by the jet stream. We know that. The strong winds in the upper troposphere, we talked about that. And the jet streams can travel pretty fast. Modern day meteorologists use past weather data, weather instruments, weather satellites, and really big computers to attempt to forecast the weather. They're relatively accurate in a day-to-day forecasting, but because there are so many variables involved, long-range forecasting tends to be less accurate. If you guys look at the news, those 10-day forecasts are just kind of a rough ballpark. You can't go out 10 days and get an accurate forecast. But the 24-hour forecast is very accurate for the next day. And here we see our storm track, which is steered by the jet stream. So all the storms are going to be picked up and moved in that direction in this case because the jet stream is flowing that way. So wherever the jet stream is, it really does control a lot of our weather. It steers things. All right, last up, we got to finish this thing off because we're taking too long here. Some key features of weather maps. We got our station models, our cyclones and anticyclones. Remember which way those things bend. You have to know that. Our fronts, cold fronts, warm fronts, stationary fronts, occluded fronts. And our different types of isolines, normally isotherms and isobars. And these are some key features of weather maps that I'd like you to know, and you really should know for this unit. So hopefully you guys learned some good information, and let's go practice it.